Here's an example of using a special trick to solve a trigonometric equation. So our equation is 2 sine x plus 3 cosine x equals 4. And your first idea might be to divide everything in this equation by cosine x. Because when you do that, like other examples we've looked at, you end up with a tangent here, so 2 tangent x, and the cosine cancels in this second term, so we just get 3 equals, well, 4 over cosine x, that's 4 secant x. So we still have 2 trig functions around, so this is really unfortunate. It's not clear that we're going to be able to make progress here. So let's back up. In fact, let me use undo. Let's back up a bit. If you remember, we have a trick for rewriting a sum of a sine and a cosine, so something like this on our left-hand side. We have a trick for writing a sum of a sine and a cosine using only a single sine function. And if we only had a single sine function, well, then we could finish solving this equation. So let's see. Remember how that trick worked was to use these coefficients in front of your sine and cosine together with the sum formula for sine, but running it backwards. Okay? So let's draw a triangle to figure out the missing piece of our denominators. So remember, this 2 is somehow associated with cosine of some other angle, alpha. And so that means we should put it, since it's associated to a cosine, we should put that 2 on the adjacent side, and alpha is this bottom angle here. This 3 is associated somehow to sine of alpha, so we should put 3 on the opposite side. And then we can use the Pythagorean theorem to get the hypotenuse. So square root of 3 squared is 9 plus 4, 13. So square root of 13. And that means the missing denominator here is the square root of 13. So we need a root 13 over root 13 times 2 sine x plus 3 cosine x equals 4. So this is root 13 times 2 over root 13 times sine of x plus 3 over root 13 times cosine of x equals 4. And the angle alpha turns out it's just going to be the inverse sine of 3 over root 13. Which is some messy number. I don't really want to write down this messy number over and over again, so I'm just going to call it alpha. So what we have here now is square root of 13 times cosine of alpha sine of x plus sine of alpha cosine of x equals 4. And now all this stuff in parentheses is the right-hand side of the sum formula for sine. So we can replace it with the left-hand side of the sum formula for sine. And that's sine of x plus alpha equals 4. And now we have an equation that only has one trig function, so we can solve this equation in the usual way. Start out by dividing both sides by root 13. We get sine of x plus alpha equals 4 over root 13. And then take inverse sines. So x plus alpha equals inverse sine of 4 over root 13. And don't forget to add your 2 pi k. And then for our symmetric solutions, we get x plus alpha equals, remember for sine, the symmetric solution is pi minus the principal solution, so pi minus inverse sine of 4 over root 13 plus 2 pi k. All right, now we're on the home stretch. We just need to move alpha over to the other side. So for the first one, we get x is negative alpha plus inverse sine of 4 over root 13 plus 2 pi k. And for the second collection of solutions, the symmetric solutions, we get x equals negative alpha plus pi minus inverse sine of 4 root 13 plus 2 pi k. And remember that alpha, we know what alpha is. It's the inverse sine of something over root 13. I'm not remembering at the moment. We can scroll up a bit. 3. So alpha was inverse sine of 3 over root 13. So we could, in our solutions, we could replace alpha with this inverse sine here, and then punch all this into a calculator if we needed decimal approximations. So this trick of writing a sum of sine and cosine with just a single sign turns out to be really useful for solving this sort of trigonometric equation. And this sort of trigonometric equation comes up in examples involving what's called harmonic motion. So if you're curious, you can Google that.